Now, in this section that we're going to cover now, we're going to cover Newton's law where we've got an unbalanced force, the F equals ma, right? That's what we're going to be looking at. Now, just before we start, in any problem where they don't say is in equilibrium, okay, the secret is find F net. Somehow you'll be able to find F net, either by resolving forces vertically and horizontally, you'll find an F net, or by a given acceleration and a given mass, you'll find F net. The secret is to find it, okay? And when you've got it, then it's cool, you can use it. There's a few bits and pieces that we're going to do. The main problem here is we're going to put a box on a slope, for example, and let's have a look, okay? Let's put a box on a slope first. No, just before we do that, let's just quickly go through just a recap of some of your basic stuff, okay? Remember, this is our slope, that is theta over there, this is the box. Now, they may or may not give you mass or whatever, it doesn't matter. You start them all the same way. You say, right, this is my FW. I put MW. This is FW, right? Which is equal to M times G. If you know M and you know, well, we know G, but if you know M, that's fine, you put it in. The second step here is you say, I am going to put you into components like that. This angle theta is the same as that angle there, right? So what we've got is we've now got our basic diagram. Let us now say, right, this one is going to be equal to mg cos theta. This is mg, and I know you've seen this before. So we always put the weight in and put its two components in, draw the triangle at right angle. The weight is the hypotenuse. Always remember that. The weight is the hypotenuse there. That's the hypotenuse, in other words, the longest side. The other two are going to be your opposite, your other sides of the triangle, right? Put them in. The next step is to go in and say, right, then put in F normal. Okay? F normal is the vertical reaction on the slope, isn't it? Okay? Put it in. The next thing is to say, right, now we've worked out what we can. I transfer this mg sign over here, just do it in the same. I always transfer it to there, because this is where I'm working over here, okay? Now, we've now done that, and we've put in, if we know certain figures or certain numbers, we put them in and we can work them out. So first of all, we draw in our weight vertically down. We put the angle in and complete the triangle using the weight as the hypotenuse. We work out what we can there, and then we put in F normal, right? I always transfer down the slope, which is the parallel to the slope force. I always transfer it onto my block. The next thing is, look, are we given mu? Okay, I'm going to make mu red. I don't know, I just like to have the friction as red. Okay, do I have mu? Yes. Then calculate FF, which is mu times F normal, right? That's the first secret. Now, the last bit is to say, right, which way is this acting? Because the questions they can ask are as follows. Part A. Let's just think about this logically, right? Part A. Change to black. A. The box, here it is. The box is on the slope, and it's going to move down. Nothing's holding the box up. What is acting to keep the box there is friction, isn't it? So the friction is acting against the direction of motion. So we will say case 1, okay, there's no other forces acting. In other words, box wants to move down. Therefore, FF is up slope, right? It's correct. So that's all we have to say. There's no other forces. box wants to move down. Right? Then the next thing is we say, right, let's put a force acting up, and you will see it as they will either say somebody is pushing or somebody is pulling with a force F up or a T up. It's the same a push or a pull, right? Makes no difference. So what do? We put that in and we say, okay, now if this force and that force, okay, are acting on the box, right? If this force plus friction is equal to that, then the box is not going to move, is it? Let's think about it. We're saying that T plus the friction means the box is not going to move. The friction is still helping me, right, to keep the box up in place. So what have we got? We've got a situation like this. I know this is theory, but it is critical. We've got a tension, right? The box force mg sine theta acting down the slope over there, okay, is still more than that. Let's say that's 100 and I'm only pulling with 50, okay? Let's make it 75. Then friction of 25 can be helping me to balance it out, which means we've just stopped it from moving down the slope. Now if I keep pulling more than that, what's going to happen? The key here is always go back and say the box is going to then start moving up the slope, which means friction turns around. Okay, that's the critical part here. Those are the questions you've got to ask yourself, right? Okay, let's have a look at the at the problem that we've got. Okay, we've got here an object lies on shown on a table and it has a mass of 10 kilograms. In an experiment designed to calculate the relationship between the angle theta and the coefficient of friction, the following was recorded. Maximum mass placed at A that prevents obviously from sliding down was 2 kilograms. Also, the maximum mass that could be placed at A was found to be 4 kilograms. Calculate me the coefficient and the angle used in the experiment. Now, this is quite a long process, but let's just start it by drawing in what do we know. Let's first of all say, right, here we go. Okay, let me just get this down. Okay. Okay, we've got this, right? So first we put in FW, and FW was going to be equal to 10 times 9.8, which equals 98 newtons. Okay. Then what did we say? We said next, put in the components, right? There's my 90 degrees. Therefore, this one, now, just go back, theta over here, and theta over there, right? That's theta. So therefore, this component here, this one, the vertical, is going to be 98 cos theta, isn't it? And this one is going to be 98 sine theta. What do? We then say, okay, there we go. There's my 98 sine theta there, over there. That's that force. I've transferred it. And my F normal, okay, is going to be 98 cos theta is F normal, right? Okay. Now you can see there's nothing holding me up the slope at this point, is there? There's no ropes up the slope or nobody pushing it. All we're doing is we're looking at this friction situation, except I've got here now a mass going over a pulley, okay? And what we were doing is we were putting different masses on there, right, to see when it slipped, when it stopped slipping, and when it moved. So we're actually finding the points on the slope where the friction is balanced. Okay, that's what we're doing. So let's see here. Right, the prep work is done. Right, do we have frictional force? Yes, we have frictional force, but we don't know mu. Okay, therefore we say, okay, let's go back to the red. I say F is equal to mu times F normal, which is equal to mu times 98 cos theta. Okay? So we've got that. Now we're given two scenarios. Scenario A, let's just make a note of this. Scenario A is the first one. The minimum mass at A was 2 kilograms. At A, 2 kilograms. B, maximum was equal to 4 kilograms. Right. So what does that mean? Okay. In scenario A, ask which way the block moves. The minimum is placed at A. The block wants to go down the slope, right? So let's have a look at scenario A first. The minimum at A we placed was 2 kilograms. Well, what does that mean? It means that over here, that force over there is 9.8, okay, times 2, isn't it? Right? Which is going to be equal to 19.6 newtons. Okay? So the tension in the rope is equal to 19.6 newtons. Okay? Now if we look at that, okay, let's just break that down and say, right, then it means that I've got 19.6 newtons acting up, and we've got mg cos theta acting down, right, which is in fact going to be 98 cos theta, right? Okay, we've got this force here, there, 98 sine theta acting down, okay, mg sine theta, mg sine theta acting down. Why have I got you as mg cos theta? Okay, let me just take you over here, g sine theta, 98 sine theta acting down like that, and 19.6 up. And I know that friction is helping me this way, is going to be, FF is going to be 98 cos theta, okay, times mu, right? Because I am in equilibrium, I am not moving up or down. The weight, the mass that I've placed at point A is just balancing out, the weight pulling down, and friction is helping me, right? It's acting in the same direction because it wants to move that down there, right? So I've got that scenario, right? If you look at scenario B, in scenario B, you've got the maximum mass. Now what has happened is you've got 98 sine theta acting down, and the friction is reversed, 98 cos theta times mu. There's my FF, right? And now what is T? T here is going to be equal to 9.8 times 4, which is 39.2 newtons, right? So what are we setting? We're setting up, because they've given us two scenarios, we're setting up two simultaneous equations. That's what we're doing with this one. Okay? Let's have a look at this and say, okay, therefore, what can we say? We can now say, okay, the force is parallel to this upslope. In scenario A, the upslope must equal the downslope. Therefore, we can say that 19.6 plus 98 cos theta times mu must be equal to 98 sine theta, and that's equation 1. And do the same for the other one. We say 39.2, okay, which is that, must be equal to mu times 98 cos theta plus 98 sine theta, okay, right, because they're acting the same way. And then we go about and we solve those two simultaneous equations, okay, and we end up, and I'm not going to do the maths, but we end up with basically theta is going to be 17.46 degrees, and we end up with mu equal to 0.1 1048. Okay? So conceptually what we've done is we've equated the up and the down because they're at equilibrium. Okay? In order to work out two equations, two unknowns. That is quite an intricate problem. Okay? If I just want to have a look at another one. Let's take this problem here where we've got two forces or two blocks on a table, and we've got them balanced. We've got forces actually on either side. So essentially we're looking at something like this, right? I've used two blocks here. I've used A and I've used block B. Okay? And it says in the figure above, A has a mass of 10 kilograms, so that's 10 kgs, and B a mass of 5 kilograms. All right, then this goes over a pulley over here, down to, and has a C. These are joined here, like that, and that goes down to point D, like that, right? And it says the coefficient of friction between A and B in the surface is 0.25. Right, so given mu equals 0.25, we know that. A and B are joined to Wasserstein. If a 5 kilogram mass is placed at C, right, 5 kilogram mass is placed at C. Calculate the mass that needs to be placed at D to keep the masses A and B on the table. Right? So, we say, all right, now let's just take it step by step. First of all, let's just break this down into we say put in FW is 10 times 9.8 is 98 newtons, okay? And this is block A. And we'll take block B over here, just draw it a bit smaller, and put in FW. And we know that they are joined with a rope like that, with a T and a T over there. Correct? That's quite straightforward. And we say, let's have a look, 98, 49 newtons, like so. And we can say that what have we got this side? This side over here, we've got a tension, and this side over here, we've got a tension as well. All right? Now, let's have a look. First thing we said, right, we put in the weight. We've done it. It's not at an angle, so we just leave it. Now, the second we said, put in F normal. F normal is 49 newtons. F normal over here is 98 newtons. Okay? What do we do next? Next, we say, right, look for a mu. Have they given mu? Mu was given as 0.25, right? If mu is given, calculate FF. So we said FF for this guy is going to be equal to 0.25 times that is going to be 12.25. And FF for this guy is 0.25 times 98, which is going to be 24.5 newtons. Okay? So all we've done is we've just followed the recipe. We calculate what FF is going to be. All right? This point, we're not really that worried in what they've asked us yet, because these are the key elements to solving this problem, right? So let's have a look. We've now got those two forces. Right, what else do we know? Okay, they said to us, which way is this going to move? Right, now let's read the question. The question says, question 1, if a 5 kilogram mass is placed right, so we can go now to this point over here, right, at C. That is 5 times 9.8, and that's going to be 49. Right? So we've got 49 newtons acting down on that side there. Right? Now, it says here, the question that they're asking us is this. They're saying, if the 5 kilos is placed at C, calculate the mass that needs to be placed at D to keep the masses A and B on the table. So what are we saying? we're saying we've got 2 blocks on the table here. Okay, over that side I've placed 5 kilograms. Now we say, which way does this want to move? It wants to go that way off the table, doesn't it? Which means then we can put friction in. We can say, right, FF is acting that way. And we say 12.25 and 24.5 newtons. You see that? What we've said is, let's see which way. We've worked friction out, now ask which way. We've placed a mass there, it's going to pull us off the table. So I want to place a mass this side, but the friction is acting, okay, against the direction of movement, isn't it? It's trying to keep the blocks on the table, right? So therefore, we can say that. And to keep it on the table means that it must be in equilibrium, correct? All right? If it's in equilibrium, now it means that the forces pulling it off the table must be equal to the forces keeping it on the table. Right? It is in equilibrium because they said to keep it on the table, which means implied it's not going to move. Therefore equilibrium. Equilibrium, therefore force pulling off the table must equal forces keeping on the table. Isn't that so? Right? So now that's quite straightforward because we can say, therefore, at equilibrium we don't need to include that tension between the 2 blocks. We can then say, have a look, this 49.2 is there. So we've got, let's call this T1. Therefore T1 plus 12.25 plus 24.5, right? That one plus that one plus that one. In other words, this one plus the friction that's acting the same way must be equal to 49 newtons acting that way. All right? Just let me make that a little nicer. 49 newtons that way. Okay? Therefore, T1, that force, is going to be balanced out, and it's going to be, T1 is going to be equal to 12.25 newtons, right? And at the end of the day, if I go and draw a little free body diagram on that side, we've got the mass over here, which is 9.8 times the mass that we're placing at D, I think it is, okay? That must be equal to T1, because it's not moving, okay? So what we've got is we've got that scenario, therefore 12.25 must be equal to 9.8 times md, therefore the mass that we can place at D is going to be 1.25 kilograms. Okay? Contrary to what most people think, they think if I put 5 there, I have to put 5 there. No, we don't, because friction is acting to stop us going off the table. So we don't need to have the full mass. If it was frictionless, yes, obviously then in that scenario, we would be able to, or we would say that in that case they are equal. The next part of this question is they say, assuming we place the mass calculated above a D, calculate the tensions in the strings. All right? Right. So, well, now let's have a look. Okay. We've got the mass of 1.25. So now if we just quickly go back, in order to save time, let me go back to this guy here now. Right? You can see here, we've got that already. Now I'm saying that we're putting 1.25 kilograms down over there, aren't we? Okay? We're putting 1.25 kilograms there, right? So therefore, it's in balance, isn't it? Which means that over here, the 1.25 times 9.8 is 12.25 newtons. This must be 12.25 newtons, which means T1 is 12.25 newtons. But now let's have a look at what T is, right? The tension between them, right? We've got 12.25 newtons acting that way, a block. We've got a tension there. Let's call that tension over there T1 and T1, because it must be the same, right? And then we've got the other block here, and we've got over there, we've got a force of 49. In other words, they want us to calculate what that T is. But remember that we've got friction acting in this situation of 12.25 and 24.5. Right? So now if we just look at block A or B on their own, let's just have a look. It means we've got T1 there, 12.25 newtons that way, but hold on, we've also got another 12.25 this way of friction. So therefore T1 is 12.25, okay, whoops, 12.25 times 2, which is going to be equal to 24.5. 24.5 newtons, okay? Right. And let's look at this side just to check. We've got T1 that way plus 24.5 must be equal to 49. Therefore T1 is going to be equal to 24.5. Okay? So the tensions are different in all three of the ropes, right, which we've now proven. Then they say we now place a 10 kilogram weight at D, calculate the acceleration and the tensions in all the strings. Right. Now let's calculate that one. Okay. Let's just add another page to it. Okay. They say calculate the acceleration, the tension in all the strings. Right. Let's go. Okay. 1.25. Okay. I'm just going to quickly redraw it. Okay. Here we go. This is A. This is B. Okay. There we've got T1. Well, we've got a T between. Just do this first. There's the table. Over here, we've got 49 newtons because that is 5 kilograms. And on this side over here, okay, we said we put a 10 kilogram here now, right? Which means that's going to be 98 newtons pulling down that way, isn't it? Now, next question is, right, we've put in what we know. Let's just link that up like that. Now we say to ourselves, okay, what's going to happen? Well, what is going to happen here, right? What's going to happen is the 10 kilogram is now going to be more. It's going to want to pull it off the table, isn't it? So, which means it's going to be pulling this way now. So if it's pulling that way, what happens to friction? Right? Friction reverses, doesn't it? Because it wants to come off the table this way. Remember, previously it was going to go that way, and we put our 1.25 here, which balanced it. Now we've put 10 over here. Now obviously it's going to want to pull it off the table that way. So if friction is reversed, okay, then it means that the frictional forces of 12.25 newtons and 24.5 newtons are reversed. Okay? Well, what is the total, okay, pulling, okay, what is the total, let's work out now, say to ourselves, right, what is the total force pulling off table, which means to the right? Okay, it's going to be 98 newtons. What is the total force on table? Okay, keeping us on is 49 plus 24.5 plus 12.25 newtons, right? This is keeping us on, this is keeping, and this is keeping us on the table. Those are the forces that are keeping us on. Therefore, we say, okay, do we have an unbalanced force now? Well, let's add that up. That is total keeping me on the table, 85.75 newtons, right? There's more pulling me off than keeping me on. Therefore, we say unbalanced force, yes, therefore F net. If I've got an unbalanced force, we've got an F net straight away, which means we have to go and we have to use that F net. That's the critical part. If you found an unbalanced force, use it straight away. That is equal to MA. How much is the unbalanced force? Well, it's 98 minus, it's 12.25. Now, here's the critical element of this. Right? We know that the F net, in other words, the force pulling me off the table, which is the unbalanced force, is equal to MA. What is M? Well, this force is acting on the whole lot of the weight, isn't it? It's pulling everything off the table, not just the bit it's attached to. So the F net applies to the whole mass, which in this case is 30 k's. Therefore, A is going to be 12.25 over 30, which is 0.408 meters per second squared to the right. Okay, that's critical that we give it a direction. Okay, so, well, what did we say? We've said, all right, so all of these, the net force is pulling me off the table, right? Now I go to each block in turn, all right, and I look what's happening to him, and I say, right, let me have a look. Usually go to the outside ones. Let's have a look at the weight on the side there first, right? Remember, we had this one on the left. We had 49 newtons acting down over there, okay, and we had a T1 over here, right? That is the force on that side. I just want to put. But this guy is going up at acceleration 0.408 meters per second squared. Okay? It's going up at 0.408 meters per second squared. I just want to rearrange myself on my chair. 0.408, right? So what does it mean? It means that this block here, the T, this tension up, is more than the weight down because it's going up, isn't it? Okay, it can't be equal, otherwise it'd be standing still, which means that the tension pulling the block up is more than the weight down. Therefore, now here's the key. You've worked out the acceleration of the system. The whole thing is moving that way. Go to the outside, put the acceleration in, and then say F equals MA. Therefore, F is going to be, now take the M of this guy, which was 5, because its weight was 5 kilos. Right? So it's 5 times A. Therefore, the force is 5 times 0.408, and it's 2.04 newtons. Right? So T2 we've got to work out now. Right? So we say, okay, is T1 up there more than the weight down? Yes, it's more than the weight because it's going up. Because if you pull with more than down, it's going to move up. It's not in equilibrium, remember. So we say, right, now we say, okay, well, if it's more, by how much more? It's more by 2.04. Therefore, T1 is going to be 49 plus 2.04, right? Because T1 is bigger than down, and it's bigger by that amount, which is going to give us 51.04 newtons. 51.04 newtons, right? So that's the tension 1 pulling upwards, right? I'm going to say this is a long one. It really is a long one. But there's a lot of the physics principles that are involved in this. Okay? And if you can master this one, any ones of the above or the others will be fine. Let's move up a bit further now, all right? So now we know that. Now I say go to the opposite side, right? And I say, okay, hang on, let me draw you. I'm going to call you T2, okay? And I've got a 10 kilogram here. Therefore, FW is going to be 98 newtons, right? Now I say, but hold on, okay? Sorry, just stick with green. Hold on. I'm accelerating down with an acceleration of 0.408 meters per second squared. Therefore, F equals ma. F is equal to 10 kilograms times 0.408, right? Which gives me 4.08 newtons. Now, down is more than up, right? Which means that the weight is bigger than the tension because it's pulling me down. If the weight is bigger than the tension, by how much? By 4.08. Therefore, T2 must be 98 minus 4.08 because it must be less by that much. And I get 93.92. Okay, 93.92 newtons is going to be that guy. 93.92 newtons because it's moving down. The tension in the string isn't enough to balance the weight, and it's out by that amount. Okay. Now, lastly, we can go to any of the blocks. All right. And I know this has been a very long one. Let's look at mass A. Shall we? Let's take mass A out. Okay. Remember, it's 10 kilograms. There's our 98 newtons. That's FW. Remember, we had F normal, right? Then we had a frictional force of 24.5 newtons because it's trying to keep it on the table. Remember, the 10 kilograms is too much. It's pulling it off the table, isn't it? Right? So what have we got there is that. And we've got over here, we call this T3. Okay? Now, have we worked out T1? Yes, we have. T1 is equal to 51.04 newtons. Right? Let's go find it. There we are. 51.04 newtons. Sorry, that's a bit ugly over there. So let me just make it a bit tidier. 51.04 newtons. Okay? Okay? There. Friction is there. That's there, T3. So the only thing that we don't know is T3. So we say, whoa, but hold on. We do the same trick again. We say the acceleration this way, A, is equal to 0.408. You've got A. You say F equals ma straight away. In this case, it was 10. So it's going to be 4.08 newtons, m times A. Right? Now let's just logic this out because it's actually quite straightforward. What do? We say, look at the situation. The block is moving this way, which means T3 pulling it this way must be more than the forces in the other direction. More by how much? 4.08. So T3 must be equal to 4.08 plus that, which is going to be 4. So T3 is going to end up to be 79.62 newtons, right? And if you go and do exactly the same now with the other block, with block B, and go and work out what T3 there is, you'll find that it's exactly the same. As I say, that was a long one, but I think we got through a lot of the physics, the mechanics side of it in just that one. I will do one more, which is a shorter one in the next one, which is just basically looking at a simple one on a slope.